All right, welcome back to differential equations here. So we are going to be talking about inverse Laplace transforms today. As usual, you will have access to a chart. Okay, so you're expected to be using this as you're doing it. So should I memorize this? No, absolutely not. You should be using this. You should get familiar enough with it so you could figure out the ones that are going to happen pretty commonly quickly. That's pretty much 1, 2, 3. Not so much for the gamma function. So this is it's like how you take a factorial when it isn't an integer. Square root, this might happen. I don't think this is going to happen too often. Sine and cosine, absolutely. T sine, T cosine, absolutely. Not so much 11 and 12. Okay, hyperbolics. I'd recommend like don't do the hyperbolics at first. Like get more familiarity with it, and then go ahead and get fancy. Same thing with 19 and 20. 21, 22, yeah. 23. This is something that this is a pretty common one. Okay. And then the derivatives down here. Okay, so we're not looking at all of this all the time, but yeah, there's a handful that tend to come up over and over and over again. Number 2, that you'll get used to. Okay. So you're expected to be using the table. Okay, it's my expectation that you're going to have one. When we do our quizzes, I will insert the Laplace transform table as like problem number 5. It'll be a true-false question. The answer is true, and you'll be able to access it from there and work your problems with having this available to you. Okay, so inverse Laplace transform. So we want to do inverse 1 over s squared minus 720 over s to the 7th. Now, the first thing I'm looking at is 720. Like, that's an awfully suspicious looking number. I know that 5 factorial is equal to 120. 6 factorial, multiply this by 6, this is 720. 6 factorial, 720. What a lucky break. So this is 1 over s to the 1 plus 1, right? Minus 6 factorial over s to the 6 plus 1. Let's see if we could find those and match those up. Oh, if you look at this, 1 factorial over s to the 1 plus 1, that would just be t. And 6 factorial over s to the 6 plus 1, that would be t to the 6th. So the inverse Laplace transform of this, right back into t, it's going to be t minus t to the 6th. All right? They get harder, I promise. Okay. But that's what you're doing. You're matching these things up. Eventually, we're going to be forcing them to look the way that we want, and then we'll be dealing with that. So the next one's also pretty tame. Inverse Laplace transform. 1 over s squared minus 1 over s plus 1 over s minus 4. So s squared, right, we know that this is s to the 1 plus 1. There's a 1 factorial here. You don't have to match them up this exact, by the way. Okay, and then we have 1 over s minus 4. It's a linear operator, so we can go ahead and just take there's a plus or a minus between them. We can just go ahead and take them inverses without thinking about it, without too much stress. Okay, 1 over s, that's 1. It's constant. Okay, so if it was 7 over s, it would be 7. Okay, in t space. So we have what? We have t, that's here, t to the 1, right? Minus 1. And then we need an s minus a. Oh, here's an s minus a. Looks like e to the at. Okay, so this is going to go back and it's going to be plus e to the 4t. Remember, there's like a, right, e to the at. So a is 4. If it was a plus, right, we'd have a minus 4 here. Okay, so there we go. All right, let's see here. How about the Laplace transform or inverse Laplace transform of 6 over s squared plus 49? Well, let's take a look. S squared plus an a squared, that's pretty, right? That's pretty nice. Except the a up here has to match the a down there, and it doesn't. So we're going to have to fix that, right? So what we're going to do here is we're going to say, well, if only this was a 7. So since constants can float out, right, that's going to do this. Inverse Laplace transform, inverse of 1 over s squared plus 49. What if I multiply this by 1? Right, that's 1. And then I'll put the 1 in, the 7 on top inside. And I'm just going to pull this on the outside. So this is 7 over s squared plus 49. Okay, so that's 6 over 7. What was this Laplace transform, right? This was this was a over s squared plus a squared. So sine of whatever's on top here, sine of at. All right, and there we go. Again, I promise they get harder. Okay, but for the first little bit, this will work. How about Laplace transform of, this is 5s minus 8 all over s squared plus 16. Okay, that's 4 squared, isn't it? So why don't we say something like, this is Laplace transform of 5s over s squared plus 16 minus 8 over s squared plus 16. Okay, this is what I mean by don't try to get too fancy with it too fast. I don't have like an as plus b. I got 2 as here, so maybe, but there's a square down here. We don't have that. So I'm just cautioning you, like don't go nuts with some of this. You'll say, hey, wait a minute, this could work. Like it could, all right, it really could. Let's not quite go into it that hard though. Okay. So if I pull them apart, right, do the 5a plus the 8, we've got an a with a constant in front of it and an s here. So we should, and that was backwards. So we have a 5s, right, and an 8. So it looks like a sine and a cosine are going to do us just fine. Okay, so this is going to be inverse Laplace transform. This is going to be 5 times, right, s over s squared plus 16. It's a plus. Minus 8 inverse Laplace transform. This was, it would be really nice if this was a 4, right? So it was a over a squared. So why don't we go ahead and put a 4 here and a 4 there. All right. So I'm just multiplying by 1 still, right? 4 over 4. And this is going to be 5 times, which one had the s in front of it? I think that was a cosine, wasn't it? So s squared over a squared plus a squared rather. It's cosine of at. So this is cosine of 4t minus 2 sine of 4t. Right. And there's our answer for that. Okay, so again, that's pretty tame. That's pretty nice. If they were all this nice, we would be a lot nicer, right? It'd be a lot easier. So here's where it's going to get a little bit more complicated. Okay, we want the inverse Laplace transform of 1 over S3 plus 3s. Well, most of your life now is going to be dealt with partial fractions. Okay, so this is an a over an s plus a bs plus c over s squared plus 3, right? It's an irreducible quadratic, so we get an ax plus b or an as plus or bs plus c at the top here. Okay, so if you were, remember, they're not going to go nuts. Okay, we're not going insane with this, so you don't have to remember the absolute worst partial fraction rules, but you do have to remember things like repeated roots, okay, and how that works. Okay, so it equals 1, right? So this is going to be a s squared plus 3 plus bs plus c times s, right? That's going to cross multiply, is equal to, clear the fractions, 1. Okay, so let's go ahead and do that. So it's going to be an as squared plus 3a plus a bs squared plus cs is equal to 1. Okay, so my s squared terms, and we have a plus b. These are the things with s squareds in them. How many s squareds I got over here? None. Okay, how about my s's? Okay, we got a cs. No other s's, right? How many s's I have over on this side? None. And then our constant term, okay, we have 3a equals 1. Right? That's not so bad, right? As far as like matrix equations go, if this was what we had for the most part, this would be nice. A is equal to a third. Since a plus b are equal to 0, and I know a is a third, b must be negative a third. Okay, so when I put this back together, okay, we've got inverse Laplace transform of 1/3 1 over s, right? That's what this is. This one. And then we have, well, c was 0, so this is going to be minus 1/3 s over s squared plus 3. Okay, well, 1 over s, that's the constant, right? So this is just 1/3 minus 1/3. Do I have an s over an s squared plus 3? Oh, right, we have an s squared plus 3. So a squared is equal to 3. That must mean a is equal to the square root of 3. So that was what? That was our sine. Which one had the s on top? Cosine had the s on top. Okay. Square root of 3t. And that's it. That's how we do it. Don't look at this and say, well, we can break this apart from here, right? This is 1 over s plus, wait, take the inverse Laplace transform of this one times 1 over s. Don't take, if there's a times in the middle here, don't take the inverse Laplace transforms. You need pluses, not times. All right. Let's see, that one is pretty good. This problem was a little hairy. Okay. This is inverse Laplace transform, right, of 1 over s squared plus a squared. Okay, now at this point, I know the temptation of looking at this, like, can I just do this and then this? No. Okay, remember Laplace transforms were coming from an integral. Inverse Laplace transform also comes from some sort of an integral. So when you had integration of f of x plus g of x, you absolutely broke these apart as such, right? But, and this was good. This was excellent. Well done. But if you have f of x times g of x, and you said that that is the integral of f of x times the integral of g of x, I guarantee you both of us will be unhappy. You will be more unhappy than I will, but I will still be unhappy. Okay? You're going to shed tears over your grade. So don't, if you have a times here, you can't do that, right? This is an integration by parts problem. If it was this easy, I mean, mathematicians, we're pretty lazy. We wouldn't, we wouldn't do integration by parts, right? Those problems are messy. If we could just do this, life would be easier, right? Try it. X cubed, right? If we could pull them apart, this is x squared times x. So this is going to be 1/3 x cubed times 1/2 x squared, right? There's a couple more constants. And that's equal to 1/4 x to the 4th. Well, these are not the same. 3 times 2 is 6, x to the 5th. Like, that ain't right. Okay, so no, don't do that. That's a terrible idea. So if you have this, you're like, I could just take the Laplace transform of this times that. Like, no, you can't do that. Okay, now when they gave us this problem, okay, I didn't finish it. They told us that f of t was equal to, right, at minus sine at. All right. So why don't we take the Laplace transform of this and see what we get? Maybe we get lucky here. So the Laplace transform, right, of at minus sine of at, right, that's going to be a over 1 over s squared, right, that's what t is, okay, minus, and then sine of at, right, wasn't that a over s squared plus a squared? Let's check. Sine of at is a over s squared plus a squared. Hey, that's pretty good. All right. So, yeah, I got two fractions. I got to add them together. Why don't we deal with, partial fractions here? Not partial fractions, common denominators. So this is a over s squared, and I've got an s squared plus a squared, s squared plus a squared, okay, minus a over s squared plus a squared. And what we're going to do is we're going to say, oh, we need a common denominator. So that's s squared over s squared in this one. Okay, so this is going to be a s squared plus a times a squared is a cubed minus, there's a minus, a s squared. Now, I hope you know by now not to multiply out the bottoms, unless you really have to. Okay, and this is going to be as squared, those cancel. A cubed, s squared plus a squared. Hey, isn't that, I would say it's the same thing, except for it's a 1 here instead of that. So they wanted to know the inverse Laplace transform, right, of 1 over s squared plus a squared. Why don't we do this? Why don't we multiply here by a cubed? Multiply here by a cubed. Then it fits, right? And we're going to get a t, right? That was our first one because they gave us the hint, minus sine of at all over a cubed. I suppose we could pull an a out of here, but since it's not going to come out of here, right? You can't pull this a away. Sine is not a linear transformation; it doesn't work that way, so you can't pull this a out. Okay, so since we can only pull it out of one of them, let's not bother. I'll just leave it. Okay, it's a nice compact form there. Okay, so that's how you deal with taking Laplace transforms, right? And that's the hint that they gave us. All right, so we could work through that. Yeah, I think I'm going to stop there on this one. This is like the first half of the 7.2 homework, and I'll do a little bit more in the next video. All right, there we go.